All right, let's chug on ahead to problem 2, in which a block is projected up a frictionless inclined plane with initial speed la, and the angle of the incline is 31.2. How far up the block does the plane go? How long does it take to get there? What is its speed when it gets back to the bottom? Okay, so let's go right here and say, oh fine, we're using pink. All right, so plate-dimensional speed, this block, frictionless inclined plane, it's got a mass of m, angle theta, la da 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 da, and let's draw some forces on this thing. So it's got weight, mg of course. It's got a normal force, and are there any other forces? Well, so what happened was we shot it up this plane with some initial speed, which I'll call v0, going uphill. But after that, it's just left to coast. So there's no other force acting on this while it's in flight. This is like it's sort of like a projectile motion problem. Except in projectile motion problems, you don't have the normal force in. You just have mg acting on this thing, so it accelerates at g downward. So this is actually a surprisingly easy problem. So we do a free body diagram for FBD for the mass. I'm going to do a, let's just change colors again for fun. Let's tie the screen. So there's X and there's Y, and X and Y. And so we've got a normal force like that. We've got mg like that. There is our theta. Okay. So, right, actually, so this is theta, more like it. And then we do the component breakdown. So we've got our normal force going up like that. We've got mg sine theta over there. And down there we have mg cosine theta. Now, we could do a force balance, in y along this direction, but actually, why bother? Because if we do force balance in x, the sum of forces in the x direction equals m times a. So what I'm saying here is it's going to be, well, let's just do another color. It's going to be accelerating, and I'm going to define positive acceleration that way. It's not going to be, it's going to be accelerating in the x direction, so either this way or this way. It's not going to be accelerating in y, so I can just say, plug in my lowercase a there for sum of force in the x direction is ma. Okay, so that means negative mg sine theta equals ma, which means a equals negative g sine theta. Well, that was just too easy. So now we know the acceleration on the block. It's actually accelerating downhill with the magnitude of g sine theta. So let's go back and see what our questions were. How far up the plane does the block go? Well, so again, let's go back to a couple units ago, but we have this object starting there, and it goes up the plane some distance. We can call that d, I guess, and it's got an acceleration that way, initial velocity there, and then final velocity is 0. Okay, so the equation we like to use in this situation is v final squared is v initial squared plus 2a delta, we'll call it delta x. We'll just, yeah, since x is going up there, sure. So v final squared is 0. 0 squared is our v initial squared was given, so I'm going to just leave that there for a moment. Plus 2. Acceleration here is this. So the acceleration is actually negative. This diagram actually, well, this formula is for, acceleration and delta x in the same direction, which means if they're not in the same direction, you just put in negative. The null acceleration should be negative. So, and it is. So this is all good. Negative g sine theta, and then delta x is this distance d it goes. So d. And then we want to solve for d, right? So let's see. How do we want to do this? Let's go v naught squared minus 2g sine theta times d equals 0. And so then looks like d is going to equal v naught squared over 2g sine theta. Okay, so there is part one. How long does it take to get there? What is its speed when it gets back to the bottom? Okay, so that's for part A. And then for part B, which I'll do in sort of a dark teal. Let's see, so part B, how long does it take to get there? Well, when it gets there, its speed is 0, right? So we can measure the time it takes for its speed to change. This is the change in velocity is v final minus v initial, which, since v final is 0, it's really just negative v0. And then the, let's see, so we're going to use this equation. This is the definition of acceleration. Delta v over delta t is your acceleration for constant acceleration, right? So we know our acceleration is negative g sine theta, right? Negative g sine theta is our acceleration, and our delta v is negative v naught, and then delta t is what we want to find, the time. So what this gives us is delta t equals v naught over blah, 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 v naught over g sine theta. So that ought to be correct. That's part B. So this is part A here, part B here. And then for part C, what is, let's see, what does part C say? What is its speed when it gets back to the bottom? Well, when it gets back to the bottom, it's back here again. So actually what we can do is plug in, take this equation again, okay? So for part C, we take this equation again, but now we're saying it goes all the way up and then it comes back to the bottom. So delta x is actually 0. So I'm just going to do this again for part C. Vf squared equals v initial squared plus 2a delta x. For this thing, let's switch to purple. Okay, so delta x is going to be 0, which means that whole term is going to be 0. Okay, so v final squared equals v initial squared. And if you're using this for velocity, then the reason this works is because these are squared. So initial velocity is upward, right? V naught went uphill. V final squared is v initial squared, but Vf is actually downhill. So Vf for velocity is negative v naught. But what they ask for is the speed when it gets back to the bottom, which is just going to be the same as this. So that's, the answer really is just positive because speed is a magnitude. Okay, so I'll move on to 3 in a second.